That dew on your wing this morning, the fog that delayed your departure last week, the thunderstorm that diverted your flight last summer. All of it, every single one of those phenomena, comes from the same thing. A gas you can't see, that makes up no more than 4% of the atmosphere by volume, but drives more flight cancellations than any other variable. Water vapor. It's the engine, the fuel, and the trigger for nearly every weather event you'll ever fly through. Last episode, we ended on a teaser. We talked about how heat moves through the atmosphere by radiation, conduction, and convection. And we mentioned briefly that water, when it changes phase, can move enormous amounts of heat too. Today, we're delivering on that promise. Water vapor is the gaseous form of water. It only makes up a tiny percentage of the atmosphere, varying from trace amounts up to 4% by volume. And roughly half of all atmospheric water vapor sits below 2 kilometers, that's 6,500 feet. Almost none of it makes it above the tropopause. By the end of this video, you'll understand the full water cycle, how to read moisture content on a METAR, and why latent heat is the most underrated force in aviation weather. The hydrologic cycle is the continuous circulation of water through the Earth atmosphere system. Water never sits still. It's constantly moving between the ocean, the air, the land, and back again. Water vapor plays a critical role in this cycle. It's the form water has to take to travel through the atmosphere. Let's walk through every stage. Some of these you already know. A few might surprise you. Evaporation is the phase transition from liquid to vapor. It's how water gets into the atmosphere in the first place. And meteorology cares most about one source, the ocean. About 120 centimeters, roughly 47 inches, evaporates off the world's oceans every single year. Here's the part most people miss. Evaporation requires energy. The water doesn't just float away. It has to absorb heat to make that jump from liquid to gas. Where does that heat come from? Anywhere available. The sun, the surrounding air, the ground, even your own body. Step out of a shower and you'll feel cold, even if the room is warm. That's the water on your skin pulling heat out of you to evaporate. The same thing happens with sweat. Your body uses evaporation to cool itself down. Remember that mechanism. It comes back later in this video. Transpiration is just evaporation, but from plants. It's a passive process driven mostly by atmospheric humidity and soil moisture. Here's the wild part. Of all the water that passes through a plant, only about 1% is actually used by the plant to grow. The other 99% goes right back into the atmosphere as vapor. Forests are massive humidifiers. That's why flying over heavily vegetated regions in summer often gives you higher dew points and lower cloud bases than you'd expect. Sublimation is the phase transition where a solid changes directly to a vapor, skipping the liquid phase entirely. In the atmosphere, this is when ice and snow turn straight into water vapor without melting first. You can actually watch this happen. Place fresh snow on a cold, dry, sunny day, and you'll see it shrink without ever puddling. The snow is going directly from solid to gas. It's also why frost on your windshield can vanish overnight even when the temperature stays below freezing. Deposition is the reverse of sublimation. Vapor becomes a solid directly, with no liquid phase in between. In the atmosphere, this is what happens inside cold clouds. Water vapor attaches to existing ice crystals and grows them. It's also the process behind frost. When the surface temperature drops below freezing and water vapor in the air contacts that surface, the vapor doesn't condense to dew first. It deposits directly as ice. That frost on your wings on a cold morning? That's deposition. And we'll talk later about why that's a real flight hazard, not just a cosmetic issue. Condensation is vapor becoming liquid. In the atmosphere, condensation is what produces every cloud. every fog bank, every drop of dew, every patch of mist. Whether it shows up as a fluffy cumulus at 3,000 feet or as fog blanketing your departure airport at sunrise depends entirely on the physical conditions of the atmosphere, but the underlying process is identical. Water vapor cools, can no longer stay as a gas, and condenses into liquid droplets. This is the most important phase change in operational aviation weather. Get this one right, and you can predict cloud bases, fog onset, and ceiling changes. Transportation is the movement of water, solid, liquid, or vapor, through the atmosphere. Without transportation, water that evaporates over the ocean would never reach inland to fall as rain. The atmosphere is, essentially, the world's plumbing system. And precipitation? That's what happens when those tiny condensation droplets bump into each other inside a cloud, stick together, and grow heavy enough to fall. Collision and coalescence. Once the drops are big enough that gravity wins, you get rain, snow, or whatever form the local temperature dictates. After precipitation lands, the water has options. If the ground is already saturated, it becomes runoff, flowing into streams and rivers, eventually back to the sea. If the ground can absorb it, it infiltrates, moving down into the soil. From there, it joins groundwater flow, traveling through aquifers underground, sometimes resurfacing in springs, sometimes making it all the way back to the ocean. And along the way, plants pull some of it back up through their roots, where transpiration sends it back into the air. Every drop is constantly cycling. Every cloud you fly under was once an ocean. Every raindrop on your windshield will eventually evaporate again. Air can only hold so much water vapor. The maximum it can hold at a given temperature and pressure is called saturation. Once an air parcel hits saturation, any extra water vapor has to come out, usually as condensation. We call air at this point saturated air. Below that limit, we call it unsaturated air. The trick is, that limit isn't fixed. It changes with temperature. Warmer air can hold more water vapor, cooler air holds less. Remember that. It's the foundation of everything that follows. Relative humidity is one of the most misunderstood numbers in weather. It is not a measure of how much water vapor is in the air. It's a ratio. It compares the actual water vapor content to the maximum the air could hold at that temperature and pressure. So an air parcel with 100% relative humidity is saturated. Anything less, and it's unsaturated. Here's the part that confuses everyone. You can change relative humidity without changing the actual water content. Watch this. Picture a parcel of air at sea level at 30 degrees Celsius. At that temperature, it can hold 27 grams of water vapor. But suppose it's only carrying 8 grams. That gives you 8 over 27, or about 30% relative humidity. Now cool the parcel to 20 degrees. Its capacity drops to 15 grams. Same 8 grams of actual moisture, but now the relative humidity jumps to 53%. Cool it further to 10 degrees. Now its capacity is exactly 8 grams. Same moisture, but now the relative humidity is 100%. It's saturated. Cooling air increases relative humidity even when no new water is added. Memorize that. It's how fog, dew, and clouds all begin. Dew point is the temperature you'd have to cool a parcel of air to, at constant pressure and constant water vapor content, for that water vapor to start condensing into liquid water. In other words, the dew point is the temperature where saturation kicks in. Lowering the temperature shrinks the air's capacity to hold vapor. Cool it enough, and capacity equals content. Saturation, condensation, dew. If that temperature happens to be below freezing, we call it the frost point instead, because the vapor will deposit as ice, not water. And here's the elegant part of the dew point concept. The dew point itself tells you how much actual moisture is in the air. A higher dew point means more moisture. A lower dew point means drier air. Period. This is the number that lives on every METAR you'll ever read, and it might be the single most useful piece of moisture data in operational aviation. The temperature-dewpoint spread, also called the dew point depression, is just the difference between the temperature and the dew point. As that spread shrinks, the relative humidity climbs. When the spread hits zero, the air is saturated. Look at it visually. With a temperature of 14 degrees and a dew point of 5, you've got a 9-degree spread and about 55% relative humidity. Cool the temperature down to 9, same dew point. The spread shrinks to 4, and humidity jumps to 75%. Cool it all the way to 5, matching the dew point, and the spread is 0. The air is fully saturated. Here's the key operational rule. Surface temperature dew point spread is critical for anticipating fog, but it has very little to do with whether you'll see precipitation. To get rain or snow, the air has to be saturated through thick layers aloft, not just at the surface. So a tiny surface spread tells you fog is possible. It does not, by itself, predict rain. In practical terms, when you're planning a dawn departure, look at the current temperature, look at the current dew point, and look at the overnight low forecast. If the forecast low is at or below the dew point, you should expect fog, possibly dense fog at sunrise. If the spread is already 2 or 3 degrees Celsius and the temperature is still falling, plan accordingly. This is one of the highest value uses of moisture data in flight planning, and it costs you nothing to check. Here's something genuinely remarkable. Water is the only substance on Earth that exists naturally in all 3 phases: solid, liquid, and gas, at the temperatures and pressures we encounter near the surface: ice, water, and water vapor. All 3, all at once, all over the planet. And as we mentioned in episode 5, water has the highest specific heat capacity of any naturally occurring substance. It can absorb and release enormous amounts of heat with very little change in its own temperature. Combine that with the phase change properties we're about to cover, and water becomes the most powerful heat transport mechanism on the planet. This is the foundation of every major weather event you'll ever fly near. Latent heat is the heat energy absorbed or released when a substance changes phase. The word latent means hidden because while the phase change is happening, the temperature of the water itself doesn't change. The heat goes entirely into changing the state of the water, not its temperature. There are 6 phase transitions, and they split cleanly into 2 groups. 3 of them absorb heat from the environment: melting, evaporation, and sublimation. These cool the surroundings. 3 of them release heat to the environment: freezing, condensation, and deposition. These warm the surroundings. Same direction of phase change, opposite direction of heat flow. Lock that in. When water becomes a higher energy phase, it has to take heat from the air around it. When it drops to a lower energy phase, it gives back that heat. The numbers tell the story. To melt 1 gram of ice, or to freeze 1 gram of water, you exchange 334 joules. That's the latent heat of fusion. To evaporate 1 gram of water, or to condense 1 gram of vapor, the exchange is 2,501 joules. That's the latent heat of vaporization. And to sublimate or deposit a gram, you exchange 2,834 joules. That's the latent heat of sublimation. Look at those values relative to each other. Vaporization and sublimation move enormous amounts of energy compared to melting. That's why phase changes involving vapor have such a massive effect on the atmosphere. Every gram of water vapor that condenses into a cloud droplet dumps 2,501 joules of heat into the surrounding air. Multiply that by trillions of grams in a single thunderstorm, and you start to see what's actually powering severe weather. The handbook gives one example that drives this home. An average hurricane releases 52 million trillion joules per day as water vapor condenses into clouds and precipitation. 52 with 18 zeros after it. To put that in perspective, that's about 40 times the entire world's energy consumption per day, based on 2005 figures. One storm, one day, 40 times the entire planet's energy use. That's the scale of latent heat. That's why thunderstorms grow as fast as they do. That's why tropical systems strengthen over warm ocean water. Every drop of rain you see falling is the visible signature of an enormous heat transfer that just happened above your head. Apply this. You arrive at the airport on a cold, clear morning. The air temperature dropped overnight, hit the dew point, which was below freezing, and the water vapor in the air didn't form dew. It deposited directly onto your aircraft as frost. That's the deposition phase change we talked about earlier. The handbook is clear. Frost is a real flight hazard. Even a thin layer disrupts the airflow over your wings, robs you of lift, and increases stall speed. Knowing how it forms, and predicting when conditions will produce it, starts with understanding the temperature-dew-point relationship and the phase changes we just covered. Apply this one. Evening before a planned dawn departure. The current spread between temperature and dew point is 3 degrees. Skies are clear. Wind is light. What does this chapter tell you? Clear skies and light wind allow rapid radiational cooling overnight. The temperature is going to fall. As it falls toward the dew point, relative humidity climbs. If the temperature catches the dew point, the spread becomes 0. The air saturates, and the water vapor condenses into fog. That's not a guess. That's the chapter's exact mechanism. Surface temperature-dewpoint spread is your single best fog predictor. Apply the latent heat concept to a summer afternoon. Moist surface air gets lifted by heating, by terrain, by a front, doesn't matter why. As that parcel rises, it cools. Cooling lowers its capacity to hold water vapor. Vapor condenses into cloud droplets. And here's the magic. Every gram of vapor that condenses dumps 2,501 joules of heat into the surrounding air. That heat warms the rising air parcel, which keeps it less dense than its surroundings, which keeps it rising, which keeps more vapor condensing, which releases more heat. It's a self-reinforcing loop. That's the engine inside every thunderstorm. The more moisture in the lower atmosphere, the higher the dew point at the surface, the more fuel that engine has. That's why high dew point days are convective days. That's why your weather briefer cares about surface dew points in the summer. Phase change. Latent heat. Aviation hazard. 6 things to take with you. 1. Water never stops cycling, and it does so through 6 distinct phase changes: melting, freezing, evaporation, condensation, sublimation, and deposition. 2. Warmer air holds more water vapor. Cooler air holds less. 3. Relative humidity is a ratio, not a moisture amount. It tells you how close the air is to saturation, not how much water is actually in it. 4. Dew point does tell you the actual moisture content. Higher dew point, more moisture. 5. Temperature-Dewpoint Spread is your operational fog forecaster. The smaller the spread, the closer you are to saturation. 6. Latent heat is the most underrated force in aviation weather. Condensation releases massive amounts of energy into the atmosphere. That energy is what builds thunderstorms, what powers hurricanes, and what turns a quiet morning into a turbulent afternoon. In this episode, we kept mentioning that water vapor capacity depends on both temperature and pressure. Today, we focused on temperature. Next episode, we tackle pressure. Atmospheric pressure controls everything from your altimeter setting to the development of weather systems to the density altitude that affects every takeoff. We'll cover what pressure actually is, how altimeters work, the difference between pressure altitude and density altitude, and why the wrong altimeter setting can put you hundreds of feet off your assigned altitude. If you understood today, you're ready for it. If this video helped you understand water vapor and latent heat, hit subscribe so you don't miss the next chapter. We're working through the entire FAA Aviation Weather Handbook in order. Drop a comment below. Have you ever watched a temperature-dewpoint spread close in and seen fog form right on cue? See you in the next one. Fly smart, fly safe.